Gas fuels make rotating detonation engines easier to study. Liquid fuels make them more practical, but also much harder. This review paper looks at liquid fuels in rotating detonation engines: kerosene, heptane, gasoline, diesel, ethanol, and blended fuels. The motivation is clear. Liquid fuels have high energy density, established storage and logistics, and direct relevance to aircraft and other propulsion systems. But the review is not saying liquid-fueled rotating detonation engines are solved. It is saying the hard part shifts. With a gaseous fuel, the main question is how to feed and stabilize the detonation wave. With a liquid fuel, the engine must also atomize droplets, evaporate them, mix vapor with oxidizer, and still deliver a reactive mixture at the exact place and time the rotating wave needs it. That is why the paper repeatedly returns to fuel preparation. Equivalence ratio, total temperature, pre-evaporation, droplet diameter, and fuel blending can all change wave propagation and engine performance. Small droplets and improved evaporation can help prepare the mixture. Larger droplets or poor mixing can slow or destabilize the wave. Kerosene receives major attention because it is aviation relevant. The review summarizes experiments and simulations showing that inlet temperature, equivalence ratio, nozzle design, oxygen fraction, and hydrogen blending can all influence rotating detonation wave speed and stability. The important message is not that one recipe always works. The message is that liquid fuel behavior is a coupled atomization, evaporation, mixing, and detonation problem. The review also covers heptane and other fuels. These studies are useful because they isolate spray behavior, droplet size effects, pre-evaporation, and equivalence ratio windows. But they also reinforce the same caution. Liquid-fueled rotating detonation engines need controlled fuel preparation before they can deliver stable operation across a useful range. A second major theme is mode control. Rotating detonation waves can change direction, number, and stability depending on injection conditions, fuel state, combustor geometry, and flow parameters. Liquid fuels make this harder because the fuel is not instantly ready to burn. The combustion mode depends on both wave dynamics and multi-phase fuel preparation. A third theme is cooling. Practical combustors must survive high-frequency detonation loading and extreme thermal environments. The review highlights combustor cooling as a key development area, including film cooling work, but it does not present cooling as solved. The paper's roadmap points to 4 future directions: complex fuels, detonation wave mode control, combustor cooling, and integration with turbines and compressors. It also notes interest in sustainable aviation fuels and other biofuels, while emphasizing that more experimental data and technical support are needed. The engineering takeaway is simple. Liquid fuels may be essential for practical rotating detonation propulsion, but they add the hardest part of the engine. The future is not just detonating fuel. It is preparing, controlling, cooling, and integrating the entire system. For more engineering research breakdowns, visit www.ProReadyEngineer.com.